The European Social Class for Molecule Research, CERN, is revealing subtleties of one more particle smasher today. On various events, it is more colossal, twice as significant. It has seen 3 new particles that could be useful in figuring out how our universe was envisioned and what its future appears to be. Experts at CERN have recently uncovered discoveries that turn how we interpret the universe on its head. Under the external layer of their massive experiments lies an immense spread of particles and controls so curious that they could stray far from traditional perspectives. These particles challenge the historical explanations of reality. What stupefying, privileged snippets of data are hidden inside these experiments? Could we eventually take another leap into the universe of CERN? Relax. The insights gathered could redefine our understanding of the universe, opening the door to new perspectives. A wormhole could speculatively appear out of nowhere, and the explanation would be attributed to the brilliant appraisals conducted at CERN, home of the Titanic Hadron Collider, LHC. The LHC is the world's most prominent and powerful particle smasher, located near Geneva, straddling the border between Switzerland and France. There are privileged secrets about this noteworthy organization that the world does not yet fully understand, secrets that could change how we view material science. The European Association for Atomic Research operates this gigantic, awe-inspiring instrument, which spans over 27 kilometers and sits underground. The primary purpose of the Large Hadron Collider is to give physicists the ability to test the theories of nuclear material science. This reinforces the prominent framework of the Standard Model of particle science, helping us understand the fundamental building blocks of the universe. At its core, the Large Hadron Collider works by accelerating protons to nearly the speed of light before smashing them together. These collisions produce showers of new particles, studied to uncover the principles of nature. It was through such experiments that the Higgs boson, often referred to as the God particle, was discovered in 2012. This discovery validated how particles acquire mass and marked a monumental moment in nuclear material science. The experiments conducted at the Large Hadron Collider are essential for understanding phenomena that occur under extreme conditions that resemble those shortly after the Big Bang. The data gathered can teach us more about how the universe began, evolved, and the fundamental constituents of matter. This makes the Large Hadron Collider a key player in uncovering new truths about reality, including dark matter and the fundamental forces of nature. However, such high-level experimentation at CERN does not come without concerns. Some speculate about high-energy experiments creating black holes or strange matter that could pose risks to Earth. CERN assures that all safety measures are met, and dedicated experts closely monitor these experiments. Theoretical studies confirm that any hazardous conditions are exceedingly unlikely. Through its constant research and discoveries, CERN helps us better understand the universe and demonstrates the remarkable potential of human innovation and collaboration in the pursuit of knowledge. The LHC is humanity's enduring marvel. The perplexing Hadron Collider is not just an incredible piece of engineering. It is a wonder of modern science. Built along the Swiss-French border, the gigantic collider spans 27 kilometers in circumference and extends as deep as 175 m underground. This makes it the largest particle collider in the world and one of the most critical tools in particle physics. The development of the Large Hadron Collider was aimed at probing fundamental scales of nature. The collider's primary ring, housed in a tunnel with a width of 3.8 m, contains 2 parallel beam pipes. Each pipe accelerates protons in opposite directions, driven by a series of superconducting magnets. These magnets are crucial for maintaining the protons' trajectories at speeds close to that of light. Surrounding the beam pipes are layers of cooling systems that maintain temperatures colder than outer space, enabling the superconducting magnets to function. The Large Hadron Collider relies on extraordinary magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The largest and most powerful superconducting magnets used are 15 m long and weigh 35 tons each, showcasing the immense scale and technical ambition behind the collider. The primary objective of the Large Hadron Collider is to investigate the makeup of the universe by observing the smallest components of matter. By accelerating particles to nearly the speed of light and then colliding them, the LHC allows physicists to analyze the particles created during these collisions. This process tests and expands our understanding of the standard model of particle physics, the best representation of the subatomic world. One of the pivotal goals of the LHC's experiments is to uncover the secrets of the Higgs boson. Its discovery at CERN in 2012 confirmed theories about how particles acquire mass. The Large Hadron Collider also studies other fundamental particles and forces, addressing key questions such as the existence of dark matter and the nature of the universe shortly after the Big Bang. The Large Hadron Collider seeks to confirm the existence of new particles predicted by theoretical physics but not yet observed. These experiments are crucial for potentially discovering new physics beyond the standard model, including supersymmetry and dimensions beyond the traditional three. The vision behind the astounding Hadron Collider is not just to understand the structure of the universe, but also to foster global collaboration. Scientists from over 100 countries participate in its endeavors. The LHC stands as a testament to international cooperation in the quest for knowledge. Its design and scale enable it to address the most profound questions in physics. Its purpose goes beyond pure scientific curiosity, aiming to advance our understanding of the universe while promoting global unity in science. Through this massive and complex instrument, humanity continues to push the boundaries of what is known and experienced in the quantum realm. But how does the Large Hadron Collider truly work? At the heart of CERN's research facilities, the Titanic Hadron Collider serves as a powerful tool for delving into the quantum realm, allowing scientists to observe and study the fundamental particles that make up everything in the universe. The process of particle acceleration and collision at the Large Hadron Collider is a crucial method for testing the foundations of material science. Inside the collider, two high-energy particle beams travel at nearly the speed of light before being made to collide. These beams move through tubes maintained at ultra-high vacuum, mimicking the conditions of space. Superconducting electromagnets, chilled to temperatures colder than space, steer and focus the beams to designated collision points. Along the way, these beams unleash immense energy as they collide, creating an array of subatomic particles, some of which are highly unstable and exist only for fractions of a second. To detect and analyze the aftermath of these collisions, the Large Hadron Collider is equipped with massive detectors: ATLAS, CMS, and LHCb. Each detector is designed for specific types of analysis. The detectors at the Large Hadron Collider, such as ATLAS, CMS, and LHCb, play crucial roles in collecting the data needed to advance our understanding of the universe. For instance, the ATLAS detector is designed to study a wide range of phenomena, from the Higgs boson to supersymmetry and extra dimensions. The CMS detector, on the other hand, focuses on similar goals, but with a different design to provide complementary insights. The LHCb detector specializes in investigating the slight differences between matter and antimatter by studying particles containing beauty quarks. These differences could help scientists explain why our universe is dominated by matter, despite theories suggesting equal amounts of matter and antimatter were created during the Big Bang. The experimental data collected by these detectors are analyzed by scientists worldwide, collaborating through CERN's extensive network. This data not only tests the predictions of the standard model, but also probes uncharted territory in physics, potentially uncovering new particles, forces, or phenomena that could reshape our understanding of reality. The Higgs boson and beyond. One of the most groundbreaking discoveries made at CERN was the detection of the Higgs boson in 2012. This elusive particle, predicted decades earlier, plays a central role in the standard model by explaining how particles acquire mass. Its discovery confirmed a fundamental piece of the puzzle in particle physics, earning Francois Englert and Peter Higgs the Nobel Prize in Physics in 2013. However, the discovery of the Higgs boson was not the end of the story. Scientists at CERN are now investigating its properties in greater detail, trying to understand whether it behaves exactly as predicted by the standard model or if there are subtle deviations that could hint at new physics. For example, Does the Higgs boson interact with dark matter? Could there be other Higgs-like particles waiting to be discovered? Dark matter and dark energy. Another major focus of research at CERN is the nature of dark matter and dark energy, which together make up about 95% of the universe. Dark matter is believed to be the invisible glue holding galaxies together, while dark energy is driving the accelerated expansion of the universe. Despite their significant role, their exact nature remains one of the greatest mysteries in modern physics. The LHC experiments are designed to search for signs of dark matter particles, such as weakly interacting massive particles, WIMPs, by examining the aftermath of high-energy collisions. If such particles exist, they might leave detectable signatures, such as missing energy or momentum, in the experimental data. Beyond the Standard Model. While the Standard Model of particle physics is one of the most successful scientific theories ever developed, it is incomplete. It cannot explain several fundamental phenomena, such as the origin of dark matter, the asymmetry between matter and antimatter, and the force of gravity. To address these gaps, physicists are exploring theories beyond the Standard Model, such as supersymmetry, which proposes that every known particle has a heavier superpartner. These superpartners could help explain dark matter and unify the fundamental forces of nature. Other theories involve extra dimensions, string theory, or entirely new particles that have not yet been observed. The Large Hadron Collider provides a unique platform to test these ideas by recreating the conditions of the early universe in a controlled laboratory setting. Global collaboration and the future of CERN. CERN's work is a testament to the power of international collaboration. More than 10,000 scientists, engineers, and students from over 100 countries contribute to its experiments, sharing their expertise and resources to push the boundaries of human knowledge. The future of CERN includes plans for even more powerful particle accelerators. One such proposal is the Future Circular Collider, FCC, which would dwarf the LHC in size and energy capacity. Spanning up to 100 kilometers in circumference, the FCC would allow scientists to explore new frontiers in particle physics, from probing the Higgs boson in unprecedented detail to searching for unknown particles and forces. Impacts beyond physics. Beyond its contributions to fundamental science, CERN has had a profound impact on technology, education, and society. Its pioneering work in computing led to the invention of the World Wide Web, originally developed to share data among scientists. CERN continues to drive advances in data processing, machine learning, and medical imaging technologies. The Large Hadron Collider and its experiments inspire people around the world, demonstrating the importance of curiosity, collaboration, and perseverance in tackling humanity's biggest questions. As we continue to explore the mysteries of the universe, CERN remains at the forefront of discovery, pushing the limits of what we know and preparing us for the discoveries yet to come. Significant disclosures at the Huge Hadron Collider include the discovery of the Higgs boson in 2012. This molecule, often referred to as the God particle, is critical because it provides evidence of the Higgs field, which is responsible for giving mass to fundamental particles. The presence of the Higgs boson was predicted by the Standard Model, and its disclosure was a remarkable accomplishment, affirming long-held theoretical suspicions. Beyond the Higgs boson, the Large Hadron Collider has also been instrumental in finding a range of other particles. For instance, the collider has provided evidence for the existence of bound quarks and confirmed the presence of tetraquarks, particles made of 4 and 5 quarks, respectively. These discoveries expand our understanding of hadronic matter, which consists of particles bound together by the strong force that holds atomic nuclei intact. These findings demonstrate the power of the Standard Model and open new avenues for exploration in particle physics, offering insights into the behavior of matter under extreme conditions, such as those shortly after the Big Bang. Theoretical risks, such as strangelets or small black holes, have been subjects of public interest and ongoing assessment. Strangelets are a hypothetical type of matter that is more stable than standard matter. The theory suggests that strangelets could convert any matter they come into contact with into strange matter. The concern surrounding this theory is that if strangelets were created during particle collisions at the LHC, they might potentially convert Earth's matter into strange matter. However, extensive studies and safety research conducted by CERN and the global scientific community have addressed these concerns. Studies have shown that even if strangelets exist and were produced at the LHC, they would likely be highly unstable and decay too quickly to affect Earth's matter. Furthermore, high-energy cosmic rays, high-energy particles from space, constantly hit Earth with energy levels far higher than those produced by the Large Hadron Collider, without creating any strangelets. This general assessment suggests that strangelets are not a significant threat. The concern that the Large Hadron Collider could create small black holes comes from theories involving extra dimensions in physics. Some theoretical models suggest that high-energy collisions within the LHC could produce tiny black holes that would evaporate quickly due to a phenomenon called Hawking radiation, named after physicist Stephen Hawking. However, researchers agree that if small black holes were ever created at the LHC, they would pose no threat to Earth. The ongoing work at CERN and the Large Hadron Collider has expanded our understanding of the universe, but it has also raised fascinating and significant questions about the nature of reality itself. The experiments conducted at the LHC are helping shape the future of physics, not just by confirming existing theories, but also by potentially uncovering entirely new areas of science. The discovery of previously unknown particles or forces could reshape our ideas of space, time, and the fundamental structure of the universe. For instance, the search for dark matter and dark energy, two of the greatest mysteries in modern physics, is a major focus of ongoing research at CERN. While we can't directly observe dark matter, its gravitational effects on visible matter provide clues pointing to its existence. The LHC could help identify dark matter particles by creating them in collisions or by revealing how their elusive properties influence other subatomic particles. Similarly, dark energy, believed to be responsible for the accelerated expansion of the universe, is another mysterious force that scientists hope to better understand through experiments at CERN. Another area of interest is the investigation of supersymmetry, a theoretical framework that suggests a connection between the fundamental forces and particles. Supersymmetry proposes that each particle we know may have a corresponding supersymmetric partner particle, which could help explain some of the universe's unresolved mysteries, such as the nature of dark matter and why the Higgs boson has its particular properties. Finding evidence for supersymmetry would be groundbreaking, as it would provide a more comprehensive understanding of the universe at the quantum level. Theoretical ideas like string theory, which suggests that the fundamental particles we observe are actually vibrations of tiny strings, are also indirectly being tested through experiments at CERN. While string theory remains speculative and largely untested, any experimental evidence that could support it would be revolutionary in how we understand the laws of nature. In addition to these advanced scientific inquiries, CERN's work has practical applications that could benefit humanity. The advancements made at CERN, particularly in the fields of computing and particle detection, have already contributed to progress in various industries. The World Wide Web itself, for instance, was created by CERN's Tim Berners-Lee in the late 1980s to meet the data-sharing needs of scientists working on particle physics experiments. Advances in computing, imaging, and even medical technology that arise from CERN's research continue to have a broad impact, demonstrating how fundamental research can lead to unexpected and significant benefits. The international collaboration at CERN is also a key part of its success. Scientists from all over the world, representing more than 100 countries, work together at CERN, sharing knowledge, ideas, and expertise. This collaboration fosters an environment of creativity and innovation, where breakthroughs are often achieved through the collective efforts of a global academic community. The LHC itself is a symbol of this collaboration, bringing together thousands of scientists, engineers, and technicians to work on one of the most complex scientific instruments ever built. However, as with any pioneering research, the work done at CERN continues to raise ethical and philosophical questions. What do the discoveries made at CERN mean for how we understand the universe and our place within it? How should society interpret the results of these experiments, particularly when they challenge long-held beliefs about the nature of reality? As CERN's experiments continue to probe the deepest aspects of physics, these ethical and philosophical questions become increasingly important. The implications of discoveries at CERN could not only revolutionize our understanding of the universe, but also raise new challenges for how we interpret the role of humanity within the broader context of cosmic events. If, for example, the existence of parallel universes or the unification of forces is proven, how might that reshape our sense of identity and purpose in the universe? Similarly, the discovery of new particles or forces could have far-reaching consequences for technologies that we use in our daily lives, as well as for potential future advancements. The relationship between science and society is evolving as groundbreaking discoveries continue to emerge from CERN. While many discoveries at CERN seem abstract or theoretical, they often lead to innovations that directly benefit society. For example, advances in computing and data analysis developed at CERN have spurred improvements in various fields, including medical diagnostics, imaging technologies, and telecommunications. Furthermore, CERN's dedication to fostering international collaboration has set a model for how scientific endeavors can transcend national boundaries, uniting researchers across the globe in pursuit of a common goal. In this sense, CERN's work is not just about understanding the universe at the fundamental level, but also about demonstrating the power of global cooperation in the pursuit of knowledge. As science continues to tackle some of the most profound mysteries of existence, its influence will likely extend beyond the lab and into every aspect of modern life. The discoveries made at CERN may ultimately lead to technologies and insights that we cannot yet foresee, but they will undoubtedly shape the course of human progress for generations to come. As the LHC and future experiments at CERN explore new frontiers in physics, the questions raised will only multiply, inviting further exploration and debate. What lies ahead could redefine our understanding of the very fabric of reality, urging us to rethink our place in the universe and the potential for humanity to grasp and manipulate the fundamental forces that govern existence. The journey into the unknown continues, and the revelations awaiting us could be as profound as any discovery in human history.